So moving on, what we want to do is develop a general solution procedure for linear constant coefficient systems. And we've seen how to go through and construct the fundamental solutions matrix for distinct real and distinct complex eigenvalues already. So what we want to do now is discuss the case, what happens when we have repeated eigenvalues, or eigenvalues with multiplicity greater than 1. And what we will see is the following. Right? We'll see that there is a general method that we can use to solve our system in any case. So for repeated eigenvalues, for distinct eigenvalues, and it's actually a very, very, very beautiful way of going through and solving because it uses some concepts that we are hopefully very familiar with for single variable functions. And so what I'm going to do is get into the idea of the matrix exponential. And you may recall that the exponential function y is equal to y naught times e to the a t satisfies the differential equation y prime is equal to a times y. It's the fundamental, in some sense, definition of this function right here. And we know that the function e to the at is the same thing as the Taylor series, and this is the summation from n equals 0 to infinity of t to the n over n factorial, or a times c to the n over n factorial. And this converges for all t. In the real numbers, because the radius of convergence of this series is actually infinite. And you typically show that in a calculus 3 course. This is the 1D case. It turns out that what's in my mind amazing is that we can do this and define what's called the matrix exponential. And not only that, we can use this idea to actually get at what the fundamental solution matrix is going to look like for a linear constant coefficient ODE system of first order ODEs. Not only that, but we can actually use this in general to, if the matrix has certain properties, if it's not constant but a function of time, we can also go through and use this as long as it has certain properties. So this is going to be really amazing. But so let's consider the ND definition of the matrix exponential function. Let A be a constant n by n matrix. Then we define the matrix exponential function denoted by e to the at, which will itself be a matrix of t, call it x of t, capital X, by the following IVP, or solution, by the solution of the following initial value problem. And this is a matrix initial value problem. You see that X prime is equal to the matrix A times X with X of 0 being equal to the identity matrix. Just like the function, right, X equals e to the at is essentially defined by the differential equation X prime is equal to a times X with an initial condition X naught of 1. Only this now is a matrix differential equation. We're saying that the matrix X, which is an n by n matrix, is equal to this n by n matrix, which is constant, times this n by n matrix, which is also, the multiplication is n by n matrix, but the matrix X that satisfies this differential equation, we're saying, is exactly the matrix exponential function. And before we go through and actually develop a way of calculating this matrix exponential function for general matrix A, I want to write down the following very important theorem that I won't be going through and proving, but you could typically find proven in any linear algebra book. This is called the Cayley-Hamilton theorem. Every constant n by n matrix satisfies its characteristic equation. And this is a very important idea in the following algorithm that we'll write down. So the proof of this you can find in any linear algebra book. I can give you a reference if you want a reference. However, what does this mean? Well, let's go through and look at an example. We take the matrix A is equal to 2, 3, 1, or 4, 1. Characteristic polynomial P of lambda for this matrix will be 2 minus lambda times 1 minus lambda minus 12, which is lambda squared minus 3 lambda minus 10. If you take the polynomial of A, the characteristic polynomial of A, which is going to be the matrix A squared minus 3 times A minus 10 times I as the identity matrix. This will reduce to 16, 9, 12, 13, minus 6, 9, 12, and 3, minus 10, 0, 0, 10, which results in 0, 0, 0, 0. So this is exactly what we mean within the Cayley-Hamilton theorem. And this is rather remarkable and gives us a very, very nice way of going through and calculating the matrix exponential, using this property right here for any matrix. And it's amazing that this works for a general n by n matrix. So the next theorem that we'll write down is called the Putzer algorithm. For finding e to the at. And we'll let lambda 1 to lambda n be the, and I want to point out here, not necessarily distinct eigenvalues of the matrix A. So we really want to emphasize here that this is working if you have distinct eigenvalues, if you don't have distinct eigenvalues, if you have complex eigenvalues. This will always give you the correct matrix exponential. We have that e to the a times t is equal to the summation from k equals 0 to n minus 1 of p k plus 1 of t evaluated, or times, this is a function of t times the matrix mk, where m0 is the identity matrix and mk is the matrix product for I from 1 to k of a minus lambda I times the identity matrix. So this is what the MKs are. And the vector function p P of t is P1 of t, P2 of t, and so on and so forth to Pn of t. Here's the solution. Of the initial value problem. Defined by P prime is equal to the matrix lambda 1, 1, 0, zero, lambda 2, 1, 0, lambda 3, 1, 0, and so on. Times P with the initial condition of P of 0 is equal to 1, 0. And what I want to do is go through and just kind of sketch a little proof here of how we can go through and actually show this. And it relies very, very heavily on this theorem right here. But the idea here is the following. It's related to the Taylor series expansion of the matrix, or the normal Taylor series expansion of a scalar value, or a single value, single real value. And it's also related to the fact that the matrix A satisfies its own characteristic polynomial. So what we'll do is we'll start by defining capital phi of t as this sum right here. And then we'll go through and show that this satisfies the IVP. This is by our uniqueness theorem. We have that all we need to do is show that phi satisfies this sum right here, satisfies the matrix O to E x prime is equal to A times x with x of 0 equal to I. First thing you want to note is that we check the initial condition. phi of t equals 0 is equal to the summation from k equals 0 to n minus 1 of pk plus 1 of 0 mk times mk. And because the initial condition for p in the definition of this this p, the only initial condition here is, or the only non-zero initial condition is the first component. It means that the only non-zero initial condition, or the only non-zero term in this summation right here, will be the k equals 0 term, which gives p1 of 0 times m0, which is 1 times the identity matrix. So this function satisfies the initial condition of this matrix differential equation. And if we look to p of t now, we have that p is defined by this system of differential equations right here, which is the same thing as saying that p1 prime of t is equal to lambda 1 times p of t. And I'll omit the dependence on t here just to simplify the notation a little bit. P1 prime equals lambda times P1, and for all other, this is for I equals 1, and for all other I values, you have the differential equation P I prime is equal to Pi minus 1 prime, or Pi minus 1 of t plus lambda I times Pi. This is for t and r. And this is really incredible, because what this is saying is that we know the solution of this differential equation right here. This differential equation will just be that P1 of t is equal to e to the lambda 1 t, in which satisfies the initial condition. And then for P2 of t, right, we have to go through and solve the inhomogeneous problem. P2 prime is equal to lambda 2 times P2 plus e to the lambda 1 times t. Because P2 minus 1 is P1 of t, which is e to the lambda 1 times t. And this is a linear single O to E for P2 that is linear, constant coefficient, and inhomogeneous. So using the variation of constants formula, we can solve P2, and P2 of t will be equal to e to the lambda 1t minus e to the lambda 2t over lambda 2 minus lambda 1. In the case of distinct eigenvalues, while in the case of non-distinct eigenvalues, if lambda 1 equals lambda 2, we get that p2 of t is just going to be t times e to the lambda 2 t. Right, so regardless of whether we have distinct eigenvalues or non-distinct eigenvalues, we can go through and directly determine all of these functions p in the vector p. And what's really nice about this is that we're going to see that using these vector functions and the properties of these vector functions, we can directly go through and show that the matrix phi satisfies the differential equation. So let's consider the difference between the matrix phi of t and a times phi of t. If we can show that this is equal to the zero matrix, then we're done. We've shown that, not phi of t, but phi prime of t. So if we can show that this is equal to the zero matrix, then we've shown that phi satisfies this differential equation and is thus the equivalent to the matrix exponential of the matrix A. So this will be the derivative of the finite sum from k equals 0 to n minus 1 of pk plus 1 of t times mk minus the matrix A times the summation from k equals 0 to n minus 1 of pk plus 1 of t times mk. This is the same thing as the summation from k equals 0 to n minus 1 of pk plus 1 prime of t times the matrix mk minus the summation from k equals 0 to n minus 1 of pk plus 1 of t times the matrix A times mk. Using what we know about P naught and all of the pKs above P naught, this is the same thing as P naught prime of T times, or P1 prime of T times M naught plus the summation from k equals 1 to n minus 1 of pk plus 1 prime of t times mk, still minus the summation right here. And using the definition of the pKs, we know that P1 prime will be lambda 1 times P1 of t times m naught plus summation from k equals 1 to n minus 1 of lambda k plus 1 p k plus 1 of t plus pk of t times mk still minus this summation right here. So let's go through and see how we can simplify this sum right here, this term right here. And it turns out that it is a very, very nice simplification that we can do. So I'm going to do a little aside here. Recall that matrix multiplication in general is non-commutative. In general, for two matrices A and B, A times B is not equal to B times A. However, this matrix MK is a very special matrix, and we can prove using induction that A times MK is equal to MK times A. And I'll do the first few steps of this to show you. So for k equals 0, A times M0 is A times I, which is the same thing as I times A. For k equals 1, A times A minus lambda 1 times I is equal to A squared minus lambda 1 times A, which is the same thing as A minus lambda 1 times A times A. And so I recommend going through and doing a proof of this by induction, but in order to do this you would have to show that the property at the that kth step being true implies the property being true at the k plus first step. So we can show this using mathematical induction on k. And now, so if we use the definition of mk, we have that mk is equal to the product of a minus lambda 1I, a minus lambda 2I, all the way up to a minus lambda ki, and mk plus 1 is equal to a minus lambda 1I times a minus lambda 2I all the way up to a minus lambda ki times a minus lambda k plus 1I, which is the same thing as mk plus 1 is equal to mk, because this product, matrix product, is just mk times a minus lambda k plus 1I. Which is the same thing as saying that mk times a is equal to mk plus 1 plus lambda k plus 1 times mk. And because of the commutativity of this matrix mk with a, this is the same thing as a times mk. And so in our summation from before, this summation can be re-expressed this summation right here as negative the summation from k equals 1 to n minus 1. Remember, we have here, this is pk plus 1 times amk, which is the same thing as pk plus 1 of t times amk, which is mk plus 1 plus lambda k plus 1 times mk. And so there's an amazing cancellation of terms here where lambda k plus 1, pk plus 1 times mk, all of these terms cancel with all of these terms. Lambda k plus 1 times pk plus 1 times mk. Oh, and I just realized that I have a small typo here. This should be mk equals 0 to n minus 1. It's also important to point out that the 0th term in this sum, so these terms cancel for k greater than 1, and at the 0th term in this sum, this term cancels with this right here. So what we're left with is the summation from k equals 1 to n minus 1 of pk of t times mk minus the summation from k equals 0 to n minus 1 of pk plus 1 times mk plus 1. And writing these two sums out gives us a whole nother number of cancellations. In fact, the only term that's left over is negative Pn of t times mn. And mn is the characteristic polynomial p, evaluated on the matrix A, which by the Cayley-Hamilton theorem is the n by n zero matrix. So this is equal to 0, and this summation that we started with right here is the matrix exponential of any matrix, regardless of whether or not the matrix is has distinct eigenvalues or complex eigenvalues, which is amazing because this gives us the solution, right, or the way of getting the characteristic solution matrix phi for any constant coefficient linear system of ordinary differential equations. So let's go through and solve some examples. Suppose we want to solve the differential equation x prime y prime is equal to 1, 1, negative 3, 3 times xy, where we'll call xi xy. The characteristic equation for this matrix A will be 1 minus lambda times 3 minus lambda minus negative 3 times 1, which is just the determinant of the matrix A minus lambda I. So P of lambda will be lambda squared minus 4 plus 4 times lambda plus 4. So we have repeated eigenvalues. Lambda 1 equals 2 and lambda 2 equals 2 are eigenvalues. And this is non-distinct eigenvalues. So they're eigenvalues that have multiplicity 2. Nonetheless, you can go through and calculate m0, m0, which is just I, and m1, which is A minus lambda 1 times I, or A minus 2I, which is the matrix negative 1, 1, negative 1, 1. And the vector function P or P of t is the solution to P prime is equal to 2, 2, 1, 0 times P. P of 0 being equal to 1, 0. So if we go through and solve this differential equation, we have that P1 of t is equal to 2 times P1, which means that P of t is equal to e to the 2t and likewise, remember this is with P1 of 0 equal to 1. P2 prime will then be equal to 2 P2 plus P1, which is e to the 2t, with P2 of 0 equal to 0. Which gives the solution that P2 of t is equal to t times e to the 2t. And so phi of t or e to the a times t is going to be P1 of t times m0 plus P2 of t times m1 which is e to the 2t times 1, 0, 0, 1 plus t times e to the 2t times negative 1, 1, negative 1, 1, which simplifies to e to the 2t times the matrix 1 minus t, negative t, t, 1 plus t. And from the general variation of constants formula, then we can go through and get the general solution. Xi of t will be equal to this matrix phi of t multiplied by the inverse matrix at t naught times whatever the initial condition is, xi naught. And there you have it. This gives you the way forward to solving any constant coefficient system of linear first order ODEs. There are a good number of examples in the book for complex eigenvalues as well, so distinct complex eigenvalues as well as for distinct real eigenvalues. This algorithm works for any situation that you might find yourself in. We'll go through and do a 3x3 example, which is a little bit more involved, but I really recommend going through and doing some practice problems yourself so you can kind of get the hang of how to go through and solve problems like this. So let's consider the 3x3 system where xi is x, y, z, and xi prime is 2, 0, 0, 1, 2, 0, 1, 0, 3. Times I. For some initial condition, xi of t naught is equal to xi naught. So the coefficient matrix is A, and the characteristic polynomial, p of lambda, will be equal to the determinant of A minus lambda I, which in the case of a 3x3 matrix is a little bit more complicated to calculate. This will be 2 minus lambda times the determinant of 2 minus lambda 0, 0, 3 minus lambda minus 0 times the determinant of 1, 0, 1, 3 plus 0 times the determinant of 1, 2 minus lambda 1, 0. Oh, and this should be 3 minus lambda, not 3. But what's nice is that these two terms are 0, and so we're left with the characteristic polynomial 2 minus lambda squared times 3 minus lambda. So the eigenvalues are when the characteristic polynomial is equal to 0, and that means that we have lambda 1 is 2, lambda 2 is 2, and lambda 3 is 3. By the Putzer algorithm, we have that phi of t, or e to the a times t, will be equal to p1 of t times m0 plus p2 of t times m1 plus p3 of t times m2, where m0 is I, m1 is a minus lambda 1 times I, which ends up being 0, 0, 0, 1, 0, 0, 1, 0, 1. And M2 is a minus lambda 2 times I times a minus lambda 1 times I, which is the matrix 0, 0, 0, 1, 0, 0, 1, 0, 1 times the matrix 0, 0, 0, 1, 0, 0, 1, 0, 1, which results in the matrix 0, 0, 0, 0, 0, 0, 1, 0, 1. And P satisfies the IVP. P prime is equal to 2, 2, 3, 0, 0, 0, 1, 1, 0 times P with the initial condition of 1, 0, 0. Which we can go through and solve, similar to before, to get that P1 of t is equal to e to the 2t, and when we solve for P2, we get that P2 of t is equal to t times e to the 2t, and P3 of t is equal to t negative t times e to the 2t minus e to the 2t plus e to the 3t. And so when we go through, plug this in to our form for phi of t, e to the at ends up being P1 of t times m naught plus P2 of t times m1 plus P3 of t times m2, which ultimately simplifies to the matrix e to the 2t, t times e to the 2t, e to the 3t minus e to the 2t, 0, e to the 2t, 0, 0, 0, e to the 3t. And so a general solution of this is of the form xi of t is equal to phi of t times phi of t naught inverse times xi naught. And this is the solution to the homogeneous initial value problem that we started initially. In general, if you want the general solution, ih of t, this will be phi of t times some arbitrary constant vector. But so this is very, very powerful. This is very, very cool, and we're going to see that this gives us essentially a way forward for classification of general the stability of critical points. We do have some major properties that the matrix exponential has and shares with the normal exponential function. That's that the derivative of e to the at is equal to the matrix A times e to the at for t and r. The determinant of e to the at is non-zero. And let's say e to the at is fundamental matrix. For the homogeneous problem star h e to the a times t, this matrix times the matrix e to the b times t is equal to e to the a t plus s, t and s and r, the inverse matrix, and this is a very, very incredible result that is very powerful. The inverse of the matrix e to the at is the exponential matrix of negative e to the exponential matrix of negative a times t for t and r. That if a times b is equal to b times a, so if two matrices are commutative, then e to the at times b is equal to b times e to the at for t and r. Again, if a times b is equal to b times a, then e to the a plus b times t is equal to e to the at times e to the pt for t and r. The seventh property, and one of the most interesting, I think, examples of a matrix Taylor series in mathematics, is going to be that e to the at is a times t over 1 factorial plus a squared t squared over 2 factorial plus all the way up to a to the k times t to the k over k factorial all the way to infinity for any t and r. This is the Taylor series formula, but for matrices. last property is that if P, and I'll actually use a different letter, if G is a non-singular matrix, then e to the G times A times G inverse is equal to G e to the A times G inverse. And I'm not going to go through and prove these, but a good exercise would be to go through and prove some of these. Some of them are more difficult to prove than others, but this is very, very neat. So this gives us a whole new application of many of the previous things that we've seen in mathematics. It also gives us a way forward to solving any constant coefficient system of linear differential equations. And we can also even generalize some of the ideas from the variation of constants formula in 1D for non-constant coefficient systems. So for instance, if A of t is a continuous n by n matrix function, on an interval I, and A of t times A of s is equal to A of s times A of t, which is something that you have to check. But if this is true, then a fundamental matrix phi of t is the matrix exponential e to the integral from t naught to t of A of s ds. And this can be proven a number of different ways. In the book, we heavily use the power series, the Taylor series of the matrix exponential to go through and prove this. But I recommend going through and doing it that way as well. I'm not going to go over it, but it's in the book. And this is a beautiful generalization of what the fundamental matrix, or the fundamental solution for the homogeneous problem is in 1D, but now to n by n systems of possibly variable coefficients. This is the fundamental matrix to the problem. Xi h is equal to A of t xi h, or more generally, xi prime is equal to A of t xi plus B of t. So what we've seen is that, to summarize, for a given inhomogeneous system of possibly variable coefficient ODEs, if the matrix A of t satisfies certain properties, specifically this property right here, we can go through and construct the fundamental matrix. And even if it doesn't satisfy this property, there are ways to go through and construct the fundamental matrix. But the idea here is that we have a very nice general variation of constants formula that depends on this fundamental matrix, and finding this fundamental matrix is key to solving both the homogeneous problem and the general inhomogeneous problem. There are a number of different examples that are gone through in detail in the book. But another interesting subclass of variable coefficient problems where you can find the fundamental matrix directly using the integral is if A of t is continuous and A of t times the integral from t naught to t of A of s ds is equal to the integral from t naught to t of A of s ds times A of t remember, because this is matrix multiplication, it's not in general commutative, but if these two, the matrix A and its integral commute, then the fundamental matrix phi of t will again be equal to the matrix exponential of the integral from t naught to t of A of s ds. And again, I'm not going to prove this here. But this is very interesting. And so essentially what we've seen now is that the system for the solution to constant coefficient systems of linear equations is possible to go through and get directly through this matrix exponential, and it depends fundamentally on this matrix exponential. And what we're going to use this to do is to try to first classify the stability of equilibrium points to a linear constant coefficient system, and then see what this implies for the stability of equilibrium points to nonlinear systems. And this will be in the next lecture. Thank you very much for tuning in. I hope you had a great day and that you learned something.